Now in this video, I'll be going through a practice problem that covers the questions you may be asked with relation to this particular voltage controller. I went looking for questions from top tier engineering schools across the continent, but it looks like I would have to be a student to access these questions. So I found a really good ebook on power electronics. The link is in the description, where I picked one of the questions we'll be going through today. Also stick around until the end to find out how you can submit a question you find challenging. If I get enough questions, I'll make a full-length video going through all these questions, but then if it's just a couple of them, I'll just make shorts for that.
Please stay.
Okay, so now let's take a look at the question. The single phase AC voltage controller shown on your screen has a 120 volt RMS 60 Hz source. The load resistance is 15 ohms. Determine A, the delay angle required to deliver 500 watts to the load. B, the RMS source current. C, the RMS average current in the SCRs or the thyristors. And D, the power factor. E, the total harmonic distortion of the source current.
And here we go.
To find the required RMS voltage that delivers 500 watts to a 15 ohm load, we basically use the power equation, that is P equals V square of our output RMS voltage divided by the resistance. Now when we make V the subject of this equation, we get the square root of P times R, which gives us the square root of 500 times 15. The final answer is 86.6 volts. Now if you remember from the previous video, we derived the relationship between the output RMS voltage and the delay angle. And so when we pick up that equation and substitute all the factors we have, we end up with a delay angle of 1.5 rads or 88.1 degrees. Now B, to find the source RMS current, it's simply V out RMS divided by the resistance. That gives us 86.6 divided by 15, which is equal to 5.77 amps. For C, we've been asked to find the SCR currents, which is basically asking us to find the RMS current and then the average current. And so to find the SCR RMS current, it's simply dividing the RMS current in the circuit by root 2. And so that gives us 5.77 divided by root 2 with an answer of 4.0 amps.
I like it. That's genius.
Now onto the SCR average current. As we see the equation here, we can simply substitute the variables we have and we end up getting 1.86 amps. So for D, we've been asked to find the power factor, and power factor is simply the true power divided by apparent power. That gives us P over S, and that's 500 divided by 120 times 5.77, which gives us 0.72. So for the last question, we've been asked to find the total harmonic distortion. Now if you're not too sure of what THD means, it is defined as the ratio of the equivalent RMS voltage counted from the second harmonic over the RMS voltage of the fundamental frequency. Now if you're not too sure of what that means, you find a link in the description of this video to another video that explains it very well. So basically the equation for the total harmonic distortion is the square root of I square RMS minus the square of the RMS current of a fundamental frequency, all divided by the RMS current of a fundamental frequency. When we take a look at this equation, we have all the variables except the RMS current of our fundamental frequency. We would need to take a look at this graph. From our question A, we noticed that the delay angle was 88.1, and so when we trace 88.1, we realize that our Cn or C1, which is the fundamental frequency, is somewhere around 0.6. And so to find our fundamental RMS current, it's simply multiplying 0.61 times our base current. Now the base current can simply be found by dividing the source RMS voltage by resistance, which gives us 8.0. And so 8.0 times 0.61 gives us 4.9. Now back to the THD equation. When we substitute all our values in there, we get 5.77 squared minus 4.9 squared, all divided by 4.9, which gives us 0.63 or 63%, which is the total harmonic distortion. That's it for this question. I'll leave a link in the description of this video where you can submit your questions that you find challenging. If you found value in this video, smack the like button and subscribe if you haven't already. Thank you for watching, and I'll see you in the next.